to another section on our limit and continuity from calculus. Again, my name is Redalisi Igan, as you already know. In the previous video, we looked at evaluating limits using analytical approach. This analytical approach had to do with either substitution, factorization, or the conjugate. We went through examples of that. In today's session, I'm going to take that of the numerical approach that has to do with tabulation of functions. Again, don't forget, limit is about finding how functions behave when they approach certain values, and that is the definition for limit. Let me take example 1. If I ask you to find the limit as x approaches 2 of this function given, you will simply say I can factorize this to x minus 2 and then x plus 2. I believe when I expand this, I should get back my numerator here. With that, I can just simply cancel the numerator and the denominator and have limit as x approaches plus 2. And hence, my answer is going to be 4. You realize that we first have to always check, even before we do a factorization, what do we have to check? We have to check that our denominator is never equal to 0 when you do the substitution. If it's 0, then I can do a factorization. Okay, so that's it for that. But how do we use the numerical approach, tabulation? Numerical approach, you want to ensure that the limit as x approaches 2 from the positive side, and then that of the negative side or the left side, they are equal. They have to be equal to say that is the limit of the function. Now I want to help you to understand what the right side or left side or positive and negative side mean. So look at the plain line. I have 0.0 here, I have 2 here. From this point or from any point getting to 2 from this way is on the left side of the 2, if you can picture it that way. And any numbers from this portion to this part of the 2 is the right portion of it. And right portion is the same as the positive side, left side is a negative. Now this does not necessarily mean negative values. No, it's just the left side of 2. So numbers here, let me change the ink. No, numbers here are all the left side of 2. And then numbers here are all the right side of 2, not necessarily negative numbers. So let's see how we do our table. So I have to first write as x approaches 2 from the positive side, the function x approaches 2 from negative side, and then the function. This f of x is from, f of x was given as x squared minus 4 all over x minus 2. So from the positive side of it, I can start from 1.9. If assume from the positive side, it can't be 1.9. 1.9 is on the left. I can start from 2.0. Let me check what I use from here. Okay, 2.1. 2.0 is still fine. No, 2.0 is actually 2, so I can't use 2.0 here. So assume I'm taking 2.1 here. This close to 2, but it's a bit away from 2. I can go ahead and say, let me take another point. So I want to clean this whole thing here. All right. So 2.2. So if I have 2 here, I'm taking 2.1 here. I can have 2.01 here, which is still close to 2. Or 2.001, that'll be somewhere here. 2.001 is still close to 2. I can still choose 2.0001. This is even a bit more closer to 2. So if this is a 2, I have numbers getting closer to 2. And then wherever I see x, I now do the substitutions here, substitution s, and then here. And you should get some numbers. From my table, it's as if as I get closer and closer to 2, I'm going to get 4.001 if you do the substitutions very well for me. Now let's say from the left side. From the left side, I can start from 1.9. I can take 1.9 here. It's still almost 2. I can go ahead and say 1.999, which is lesser than this, which will be more closer to 2. 1.9999. I'm just extending the 9s. This is still 2. 1.9999. This is almost close to 2. And if I do the substitutions of these values into the function of x, it is estimated to be almost 3.999. And so we can conclude that at the end of the day, the limit as x approaches 2 from the positive side of the function, and then the limit as x approaches 2 from the negative side of the function are all equal to 4. And so since they are equal, it means the limit of the function as x approaches 2 of the f of x is 2, which agrees with when we did the factorization here. So sometimes I want to be smart with the thing. But if you actually use the numerical approach, then you go through this tabulation. There are cases where the analytical may not work, and then you have only to resort to the numerical. So you take note. Example 2. Examples. We are taking 3 examples. So example 2, the limit as x approaches the function given. You realize that if I do a direct substitution from the denominator, I'll get 0. So it means I have to do something else. Can I factorize? I'm not sure I can do that. So this is where the numerical becomes important to use. In the same approach, I want to look at values close to 2 from the left side of 2, values close to 2 from the right side of 2. If I start from 2.1, I have 2.01, 2.001. If I pick 1.9 here, I have 1.99, 1.999. They are all closer to 2. So just from the first examples, I wouldn't take any extra values. What you have to do is substitute your values here into the f of x and then see what you're going to get. I've already done the tabulation in my slide. If you want to follow it from that, from slide 14, sorry, slide 2, you would realize that from the positive side of it, from the positive side, we are getting values. It is actually divergent. If you look at the trend from, let me write the answers here. It was first negative 5.9, then it became negative 95.99. We have negative 995.99, then negative 9995.99. It is divergent. It is not convergent. Unlike the first example, you realize that it was almost, I didn't write the answers, but let me go to slide 1. 3.9 from the positive side. I had 4.1, 4.01, 4.001, 4.0001. So it's almost close to 4. It's convergent to 4 because as zeros increases, we get to 4. But with the second example, it is not so. From the positive side, it is divergent. From the negative side or the left side of it, it is also divergent. From 13, we move to 103, we move to 1,003, we move to 10,003. It is also divergent. Okay, so realize that even from the positive side, the limit as x approaches 2 from the positive side of our function, the limit does not exist. If it does not exist, I don't even worry myself to look at what is happening on the other side because they have to be equal. If they're not equal, the limit do not exist. Fortunate for us or unfortunate for us, the limit from the negative aspect of it too does not also exist. And so at the end of the day, the limits of this function do not exist. Even by substitution, it will be undefined. Now the last example for the numerical aspect, let's look at 3x plus 9 all over x squared minus 3. Can I do a direct substitution? If I do a direct substitution, I'm going to get something over 0, which becomes undefined. So you must do something. Can you factorize? I'm not sure you can factorize this out. Someone said, okay, let me have 3 here, fine. There's x plus 3. And how do you factorize the denominator? It's not going to work. If it's x plus 3, x minus 3, let's see. Yeah, this should work. And then I cancel that one. I have 3 over x over 3. So I have to find the limit as x approaches negative 3 of 3 on x minus 3. You realize that this will still be, okay, negative, so I have 3 over negative 6. And that should give me 1 over 2, negative 1 over 2. as a limit. That's 0.5, negative 0.5. I hope this is clear. If I want to use the numerical approach, so there's negative 1 over 2, that's negative 0.5. If I want to use the numerical approach as our focus, we have to find on the red line values approaching negative 3 from the left post. This is the right side of it, and then approaching negative 3 from the left side of it. Okay, from the right side of negative 3, what do I choose? That's the next question. I can have 2.9 here, negative 2.9 here, and what I can have here can only be like 3.01, and I can move to 3.001, negative 3 here. So negative 2.9 here can be negative 2.99. If I move again, I can have negative 2.999. I just hope this left and right side is still clear. Okay, so from the left side of it, I have, let me start with the positive side here. So I can have negative 3.1, negative 3.01, negative 3.001, negative 3.0001. Okay, and from, oh, I think I've done a mistake. From the positive side, I have negative 2.9, I have negative 2.99, negative 2.999, negative 2.999. These are all closer to negative 3. And from the left side of it, I made it positive. From the left side of it, I have negative 3.0 first, then I have negative 3.001, negative 3.0001, and so on and so forth. And then you do the substitution to your function f of x. You have to substitute these guys into wherever I see x, and that will be the values I obtain here. So if you look at my table on slide 3, you can tell that as we substitute these values and approach a higher number, we have negative 0.5008, and then we have negative 0.4999, which is approximately 0.5. This is also approximately 0.5. And so that is how the tabulation is being done. I hope that wasn't difficult to do. So at the end of the day, the limit as x approaches negative 3 from the positive side is almost 0.5, and then the limit as x approaches 3 from the negative side is also 0.5, and hence they are equal, and that is your limit, and that confirms our initial answer. And that brings me to the end of the numerical aspect. In the next session, we're going to take that of the continuity, which is also an application of limits. So on the application of the limit, we have continuity, we have derivatives, and all this on slide 4, and we're going to take it one after the other. Thank you.